Hi students, let us proceed to part 3 of chapter 15, waves. Now here we are going to derive an expression for the speed of a travelling wave. So this graph shows the progression of a harmonic wave from a time t to a time t plus delta t, where delta t is a small interval of time. So the whole wave pattern shifts towards the right, as you can see, and the crest of the wave is denoted by a dot, and that dot moves towards the right by a small distance delta x in a time interval delta t. So let us observe the motion of the crest of the wave once again. So the figure below gives the shape of the wave at two different instants of time, which are at a time t and at another time t plus delta t. So there is a small time interval of delta t between the two wave patterns. And the entire wave pattern is seen to shift towards the right, that is the positive direction of x-axis, by a distance delta x. So the crest is shown by a dot, and that dot moves by a small displacement delta x. So obviously you know speed of the wave will be displacement by time, which is delta x by delta t. Now if we put the dot on a point anywhere else, it will move with the same speed. So if it has to move with the same speed and for the wave pattern to remain as it is without changing, we need to have kx minus omega t to be a constant. Only if that phase is a constant will the waveform pattern be same. So as time changes, the position x of the fixed phase point must change. So let us see. The first expression is kx minus omega t. So when the wave started, its phase was kx minus omega t. After a time interval delta t, the phase becomes k into x plus delta x minus omega t plus delta t. But we have to keep the extra part, that is k into delta x minus omega into delta t equal to 0. Otherwise the phase will change and the waveform pattern also will vary. So if k into delta x minus omega into delta t equal to 0, then k into delta x will be equal to omega into delta t. Now limit delta t tending to 0, we can write it as dx by dt equal to omega by k, and this is equal to velocity or speed. But omega, you know, is 2 pi by period, or it is 2 pi into frequency, and k is 2 pi by lambda. Substituting these two values in velocity, we get velocity is equal to lambda into frequency, or it is equal to lambda by time period, capital T. So this is a general equation for all progressive waves. Now let us have a formula, find a formula to calculate speed of transverse waves on a stretched string. So you know, if you hold a string at one point and keep the other point fixed, and you just have you just pluck the string, you can see waves traveling through the string. So we can find an expression for speed of such waves. They are transverse waves. Now there are two factors when you calculate the speed of mechanical waves. Now speed is directly proportional to restoring force, and speed is inversely proportional to inertial properties of the medium. So when you consider a string as an example, the restoring force is provided by the tension which is formed in the string. So tension is denoted by capital T. And inertial properties are provided by the linear mass density which is denoted by mu. Now, what is linear mass density? It is mass of the string divided by length of the string. So, mu equal to mass of string divided by length of string. And the restoring force is provided by the tension in the string. Now, we are going to use the method of dimensions to get a formula for velocity here. So, you know the dimensions of mu, that is mass by length, will be ml minus 1. And the dimensions of tension, which is the same as force, it will be mlt minus 2. And the dimensions of velocity or speed is lt minus 1. I hope you remember the dimensional method that you studied in the 11th standard. Now, if you equate restoring force divide by mu, that is capital T by mu, you will get, if you use the dimensions, you will get L squared T minus 2 as the result when you cancel. Now, incidentally, L squared T minus 2 is square of the dimensions of velocity. The dimensions of velocity is Lt minus 1. So, the square will be L squared T minus 2. So, we can write V squared equal to T by mu, or we can write velocity V equal to a constant C into square root of T by mu. It is always velocity or speed proportional to root of T by mu in dimensional method. So, to remove the proportionality sign, you introduce a constant. So, speed is proportional to square root of T by mu, or speed is equal to capital C into root of T by mu, where C is a constant and experimentally it has been found to be 1. C is found to be 1. Therefore, the speed of transverse waves on a stretched string, that is V equal to square root of T by mu. Now, this table shows us the speed of sound in different media. See, look at the medium, gases, liquids and solids. In gases, we have air. The speed of sound in air at 0 degrees Celsius is 331 meter per second. And if the air is at a higher temperature, the speed increases, 343. Now, through helium gas, the speed is still higher and hydrogen still higher. In liquids, water at 0 degrees Celsius is 1402. So, in liquids, comparatively, we have the speed of sound is greater. And in solids, if you look, aluminum has got the highest speed, that is 6420 meter per second. So, in solids, sound can travel with a high speed. Now, let us work out a very simple example. A steel wire 0.72 meter long has a mass of 5.0 into 10 to the power minus 3 kilogram. If the wire is under a tension of 60 Newton, what is the speed of transverse waves on the wire? So, you have to use the formula velocity is equal to square root of T by mu, and T is given here as 60 Newton and mu is given as 6.9. That is, you have the value of mu is mass by length. Okay, so mass of the wire by length, that is mu. 5 into 10 to the power minus 3 divided by 0.72 will give you mu. Tension is given directly as 60 Newton and you can calculate V. It is found to be 93 meter per second. Now, so far we had observed or studied about the speed of transverse waves on a stretched string. Next, we are going to learn about speed of a longitudinal wave. And an example of longitudinal wave is sound. So, we can generally say we are going to learn about the speed of sound through different media. So, in a longitudinal wave, the constituents of the medium vibrate parallel to the direction of wave propagation. You know that. and longitudinal waves consist of compressions and rarefactions of small volume elements of air. So when longitudinal waves pass through a medium, it will create compressions, that is regions of high pressure and regions of low pressure, expansions in the medium through which it is passing. So this will give a compressional strain to the medium, and compressional strain is otherwise bulk modulus of the medium. Now the formula for bulk modulus is B equal to minus delta P by delta V by V. So delta P is the strain, stress, and delta V by V is the strain that is produced. So B has the dimensions of pressure, and the dimensions of pressure are M L minus 1 T minus 2. So here again the inertial property is given by mass density, that is mass by volume. So in the previous one it was mass by length, now here it is mass by volume. So again we use the method of dimensions, and we see the dimensions of bulk modulus divided by the dimensions of mass density is equal to square of the dimensions of velocity. So again velocity is directly proportional to square root of B by rho, or it is equal to a constant into square root of B by rho. Here also C is equal to 1. And therefore, the general formula for longitudinal waves in a medium is given by V equal to square root of B by rho, where B stands for bulk modulus of the medium. So this is generally for a gas or something which can be compressed. So if you consider the speed of longitudinal waves in a solid bar, then we cannot use bulk modulus, we will have to use Young's modulus of the material of the bar. So our formula changes to V equal to square root of Y by rho, where Y is the Young's modulus of the material of the bar. Now let us study Newton's formula for longitudinal waves. Ideal gas. Now, ideal gas is one which obeys Boyle's law, Charles' law, and all that to perfection. So, for an ideal gas, the pressure P, volume V, and temperature T are related by the relation PV equal to N kB T, where N is the number of molecules in volume V, and kB is Boltzmann constant, and capital T is the Kelvin temperature of the gas. Now, Newton suggested that the changes that take place in a gas are isothermal when longitudinal wave passes through it. What is an isothermal change? Now, an isothermal change means that the pressure volume changes are very slow, and also the formula or the equation followed in an isothermal change is Boyle's law equation, that is PV equal to P into V equal to constant. Okay, so these two factors are a speciality of isothermal change. It is a slow change and it obeys Boyle's law. Now, if PV is a constant, then differentiating we get V into delta P plus P into delta V equal to 0. Or if you bring P delta V to the other side, then you get minus delta P by delta V by V equal to P on simplifying. But the left side of this equation is bulk modulus. So here Newton is trying to prove that bulk modulus and pressure are same when longitudinal waves pass through a gas or in an ideal gas. In an ideal gas, the bulk modulus is equal to pressure. So he changed the formula for bulk modulus. He wrote pressure B equal to P. So he changed the speed of longitudinal wave for an ideal gas as V equal to square root of P by rho. The general one was square root of B by rho. So Newton tried to prove that velocity is equal to square root of P by rho, pressure by density. Now this is known as Newton's formula. But there was a slight inaccuracy in what Newton tried to prove. We know that 1 mole of any gas occupies 22.4 liters at standard temperature and pressure. So density of air, you know the value for density of air at STP is 1.29 kilogram per meter cubed. Alright, and we know the pressure, the value of standard pressure is 1.01 into 10 to the power 5 Newton per meter squared. So if you apply Newton's formula, then the speed of sound is found to be only 280 meter per second at 0 degrees Celsius. So this is inaccurate. This result is 15% smaller than the experimental value of 331 meter per second for speed of sound in air. So there was some mistake in Newton's explanation. So now another scientist, Laplace, made a correction to Newton's formula by considering that the pressure variations are not isothermal but they are adiabatic in nature. Now what are adiabatic changes? In adiabatic changes, the pressure variations are fast and they do not obey Boyle's law, but PV raised to gamma is a constant. PV raised to gamma is a constant. That is adiabatic, the equation for an adiabatic change. What is gamma? Gamma is the ratio of specific heat capacities at constant pressure to constant volume, or gamma equal to Cp by Cv. So now the formula or the equation starts with P V raised to gamma is a constant, and on differentiating we get delta P V raised to gamma equal to 0. So first keep P aside and differentiate V raised to gamma. So we get P into gamma V raised to gamma minus 1 delta V plus, for the second part, keep V raised to gamma as it is and differentiate P. So we get V raised to gamma delta P equal to 0. On simplifying, if you divide by V raised to gamma minus 1 throughout, you will get P gamma, P into gamma is equal to minus delta P by delta V by V. So this is the bulk modulus in an adiabatic process. So for an ideal gas, the adiabatic bulk modulus is given by B adiabatic equal to minus delta P by delta V by V, which is equal to gamma P. So Laplace said instead of using pressure equal to bulk modulus, we have to apply gamma into pressure equal to bulk modulus, and he made a new equation, velocity or speed equal to square root of gamma P by rho. Gamma for air, the value of gamma for air is 7 by 5, and on calculating, Laplace got the value to be 331.3 meter per second, which was very accurately equal to the experimental value. So this modification to Newton's formula is called Laplace correction. Okay students, now we will meet again in part 4.